So you've already figured out how you can use experimental data and solve for a zeroth order, first order, or second order reaction. There are other orders. You can go to third order. You can go, lots of different ones, but the ones that are in the scope of general chemistry 2 and the American Chemical Society expected standards are these three. So those are the three we're going to focus on, and you're going to have more videos about them and how to work the different things that I'm about to show you. But before we go there, I just want to remind everyone, you know by this point, chemistry people are really, really crazy about figuring out trends. And so if you've got a periodic chart, you already learned about like trends, electronegativity goes in that direction, size goes in that direction. So you can predict sizes and shapes using the periodic chart. Well, you can go beyond that, and you can see that we actually do this as humans normally in real life. And here's an example of where we might do it. So let's say you want to get a dog. Well, let's see. What about a smart dog breed? Well, are you looking for a smart dog breed? Then you might choose and categorize some of these dogs. But what if you were looking for a large dog breed? Well, then you might go with some of these ones. Or what if you were looking for a small dog breed? You might go with some of these ones. But also, there are some general characteristics with being a smart kind of dog. So they're going to be easy-ish to train, right? But then they're also going to be really smart, and they're going to get bored easily. So, or like a large dog, they don't have as long of a lifespan as a short dog. They tend to have really, really bellowy kind of a work unless it's been, well trained. And then small dogs tend to be the kind of dogs that, they're good companion dogs most of the time, and they're very small, and they can fit into a lot of, household situations because they're small. So you take the one piece of data and you're like, okay, this is this category, and then you can make extrapolations and piece of information about it, about the dog, and the kind of dog that you would hope to get. So we can do this with reactions, and that's the coolest thing about all this. People have already done all this work. If you've got an experiment and you just run a few little experiments, just like you saw in the homework last time, and you figure out that something is zeroth order, there's all this extra data that you can use to predict things. All of this right here comes from something being zeroth order. So you already know this rate law does, and that's a zeroth rate law order. But we have something called the integrated rate law. There's more to come on this. But what the integrated rate law lets us do is to graph it. And the reason that we like to graph things as chemistry and sciencey people is if you can get a straight line, and if you know this, and you've only done experiments for that section, you can predict what might happen here or here. And you can predict it pretty well, and other people will accept you if you can get a straight line. And being able to predict something in chemistry is where all the money is. So if you want to be a successful chemist, maybe you don't want to, but if you want to understand what is success in chemistry, it's being able to predict something and follow through and making it happen. So for kinetics, what that means is being able to relate and say, oh, this reaction will be completely finished. We'll have the most time effective, in this range. This is the most time for money cost right there. Or maybe we'll say it's in this range. That's the most effective. So you can change up reactions and scale them and change them, just being able to graph them on a line. And there's another piece of information you'll learn about called half-life. And half-life is our way of kind of saying how long will it take for half of something to disappear. And that's useful too, because it kind of helps us see, as reactions progress, they say when 10 half-lives have passed, basically there's no substance left. That's a good rule of thumb. So we will also do calculations with this time right here. So for zeroth order, you get all that information. And then first order, guess what? It has its own information, and it's not the same. So we know that's not the same right there. This one actually has a concentration in it. This looks a little weird. If you really, really, really want to understand this happens, it is calculus. It has to do with doing an integral and writing the rate as change of concentration over change of time. So if you click on one of the little plus signs and you're really interested in this, you can look at approximately how it's done in a very simplified manner. You don't have to know it for any test or anything. That's only for your own interest. You can rearrange this guy because these are on top of each other. You subtract logs, so it's ln of a of t minus ln of a0. And then you can move ln of a over to the other side by adding it. And then you get another thing that you can graph. So all of these are all graphed with respect to time. And this one ends up with a graph that kind of looks like this one, but notice I have to do the log of this one. This is a curve around if you don't take the log of it. We don't want curves, we want straight lines. And then we have a way to get a half-life. And then finally for the second order, we have these ones. Notice that's familiar. This is his set that gives us a lovely straight line. Now, I know it looks like something is increasing in time. Your reactants are always decreasing. This is having to be graphed as 1 over AFT. So your largest AFT is going to give you a small number, and then a smaller denominator gives you a large number. So, but it's just how you have to graph it to get a straight line, and we want a straight line. Oh, please give us straight lines. So this is where we're headed. We're going to do lots of math, play around with these forms, be able to predict the graphs here, and then being able to use T1 half. And cool thing on the T1 half, just a little note, the K here is the K here. The K here is the K here. So there's a common variable, so you can plug them into each other too.